Hello, welcome. Here we have this expression here, 2 to the power of 100 versus 3 to the power of 60. Which is greater? So we're going to use some simple logic in actually getting the value which is greater, because if we have to compute this without the use of calculator, 2 to the power of 100 means 2 times 2 times 2 times 2 into 100 places. And that may give us a challenge. And 3 to the power of 60 means 3 times 3 times 3 into 60 places. And that will also give us a challenge. So we're going to use a format to actually tell which one is greater. So from here, we're going to take our solution here. Now, the first thing we're going to do here is this. We want to express these two powers to be of the same quantity. Is it possible to do that? Yes, it is possible. Because we want to make use of the law which says that if you have your A, okay, greater than B, therefore your A to the power of N will be greater than B to the power of N. Okay, this is a property. Provided your B is greater than 0, then your N is also greater than 0. So for us to know if this is greater than this or this is less than this, we want to make use of this. And making use of this, we want to strike the same power for this and this. And so let's take the first one, which is this. So our 2 to the power of 100. We want to express 100 as a product of two numbers that when we multiply together will give you this. And from one of the numbers, we're going to have same thing from this other side. So 100 can be written as our 5 times 20. So this could be written as our 5 times our 20, right? Good. So if we apply the property of indices, it says that if you have your A to the power of your M times N, this is same thing as A to the power of your M all raised to N, right? So I want to separate this 5 from this 20. And so this could be written as our 2 to the power of 5 all raised to the power of 20. All right. So from this, what is our 2 to the power of 5? It means 2 times 2, which is 4 times 2, 8 times 2, 16 times 2 will give us 32, right? So we're going to have this to be 32 all raised to the power of our 20. So we have the power of 20 here. So let's see if we can get the power of 20 from this, then we check the base number. So from here, we now take the second one, which is our 2 to the power 3 to the power of 60 is equal to our 3 to the power of what? So 60 can be expressed as 3 times 20. So we have here 3 times 20. So apply the law of indices here. We can separate this to be 3 to the power of 3 all raised to power 20. And so this 3 to the power of 3 will give us 27. So we have 27 all raised to the power of 20. So thank God we'll be able to strike a deal. Now let's go to our property. Look at this property we just outlined here. We say that if A is greater than B, then A to the power of N is greater than B to the power of N. So let's check our A here. So our A here is 32 and our B here is 27. So 32 is greater than 27. So we have here 32 is greater than 27. And they both have the same exponent, and 2020. And so thus, it means, therefore, our 2 to the power of 100, okay, which is equivalent to 32 to the power of 20, is greater than our 3 to the power of 60. Okay, so this is how you prove simple challenges of this kind. Thank you. Hello and welcome to today's class. We have a math problem before us here. It's a simple question. It's a usual question, not an unusual question this time around. It's an exponential question. The question is 2 to the power of 5x plus 1 equal to 5 to the power of 2x plus 1. What is the value of x that satisfies this challenge here? So the first tool we take here is our solution. So take our solution. So if you conversate with some of the problems I solve on this channel, then you should consider this a simple one. All right. So how do we solve this here? We're going to make use of the simple laws of indices and logarithm. And so we look at the power here, we look at the power here, and we just have to rewrite the expression on this side and this side with regards to the powers we have in there here. The first law of indices we're going to apply here is the power rule of indices, which says if you have your take our p to the power of your m there plus n, this is equal to your p to the power of m times p to the power of n. How? The base alphabet here are the same, the exponents are different, and we have a multiplication sign. So the rule says we can add the power, and that's what we have here now. And so in our question, this side is given in this format. This side is also given in this format. So we want to take it to this format. So rewriting the left-hand side, we're going to have our 2, which is the base number, raised to our 5 to the power of x, times our 2 again to the power of 1 here. They're equal to, we do same thing here, which is 5 to the power of 2x there times our 5 to the power of 1. Okay, now let's check out this here. Yeah, we want all the terms that are having x at the exponent to be on the left-hand side. And how do we go about that? Look at this expression here, or this term here, 5 to the power of 2x. We want to divide through by 5 to the power of 2x. So divided through, we're going to have here 5 to the power of 2x. Then we equally divide this side by 5 to the power of 2x. And again, we want the constant terms to be on the right-hand side. Here we still have a constant term without an alphabet or without a variable. So we move it to this side of the equation. And how do we do that? We divide by our 2 to the power of 1, which of course is 2. And so we can say here times our 2 to the power of 1. Then we call it, multiply this 2 to the power of 1. So let's cancel out and see what this gives us here. So you discover that this will go with this, and on this other side, this will go with this. Okay, so we are now left with our 2 to the power of 5x all over our 5 to the power of 2x. This is equal to, we have 5 to the power of 1, which is 5 all over, and the denominator 2 to the power of 1, which is 2. This is easy, right? Good. Now look at this expression we have here now. This is base 2, this is base 5. And at the exponent, the expression, this term is different from this term, but we have something common here. The variable is common. So we have x here, we have x here. We're going to rewrite these two expressions here. Apply the simple rule in indices. First one, which says again that if you have your p right to the power of your m times n, this is same thing as your p to the power of m. We can put this in bracket and raise it to n. So if we use this power to multiply this, it will give us this back, right? So I want to separate this x from this 2 to the power of 5. Also separate this x from this 5 to the power of 2. Okay, so we're going to have this to be our 2 to the power of 5 all raised to the power of x all over our 5 to the power of 2 all raised to the power of x equal to our 5 all over 2. This is easy, right? Good. Now, what we do from this part here, it is pretty easy again. We are having this to the power of x, we are having this to the power of x. We apply another rule again. We say that if you have your p to the power of your m all over q to the power of your m, then this is same thing as p all over q all raised to the power of our m. Because the law says that when you have quantities inside a bracket and all raised to a variable or to a constant, then we can use the power to affect or distribute the power on the powers, on the exponents of each of the terms inside. Okay, so with this, we can rewrite this expression here. So let's take to this side. So this could be written as 2 to the power of 5 all over 5 to the power of 2 all raised to the power of x equal to our 5 all over 2. Wow. Now let's check out something here. If we decide to take 2 to the power of 5 to bring out the value, and we decide to bring out the value of 5 to the power of 2, it will make no difference as far as this challenge is concerned. So let's leave them in that form which they are. So how do we get this? We just have to take the log to base 10 or ln base e. Okay, yeah, let's make use of the ln base e here. So from here, want to ln this side, so have the ln of bracket our 2 to the power of 5 all over 5 to the power of 2 all raised to the power of x is equals to the ln base e of bracket 5 all over 2, close bracket. So we apply the first rule of the power law of logarithm, which says if you have the ln of your p all raised to the power of q, then move this q back to give us here our q times the ln of our p. All right, so if we have this, then we can move this x back to this side. So we're going to have x times the ln of bracket open 2 to the power of 5 all over 5 to the power of 2 close bracket equals to the ln of r 5 all over 2. This is pretty easy, right? Good. So what do we do next here? We are looking for x, so we just have to make sure that x is standing on its own. In other words, let's divide through by the x. So we're going to have this all over the ln or bracket open 2 to the power of 5 all over 5 to the power of 2 close bracket. Then we equally divide this by this same quantity, because whatever you do to the right hand side, you must do to the left hand side, or whatever you do to the left hand side, you must do to the right hand side, close bracket here. So this will leave the system. So we're not having our x will not be equal to. Now let's check out this. We have what we call the division law of logarithm. Here we have 5 all over 2, suggesting a division. And here 2 to the power of 5 all over 5 to the power of 2, okay, it's also a division. So what does the division law say? It says that your ln of your p all over your q is equal to the ln of your p, okay, p minus the ln of your q. Okay, so if we apply this rule to this, then we're going to have this to be the ln of our 5 in bracket minus the ln of our 2 close bracket all over the ln of our 2 rather to the power of 5, then minus the ln of our 5 to the power of 2. Wow. Again, remember the power law of a logarithm. Have we searched that out? Yeah, look at it here. So we have it here. So we can apply the power law of logarithm to this and to this. And so we're going to have, therefore, our x in R will give us the ln of bracket open 5, then minus the ln of bracket open 2 all over. This is going to give us our 5 times the ln of 2 close bracket minus 2, then to the ln of our 5 close bracket. So this is the final answer in our solving today. Okay, so if you put this into your calculator, you have numerical value, okay, which we can put in here, but it's going to give us an approximate value. Okay, so this brings us to the end of today's class. Thank you for being there. We have a radical challenge here. This equation is a simple one, it's an easy one if only you are familiar with the rules that governs indices. So we're going to make use of some of the simple rules that actually guide the operation in indices here. So the question is the square root of, under it we have your 3 to the power of x, all further raised to the power of 2, equal to 3 to the power of root x. What is the value of x here? How many values or solution we're going to get from this challenge? Okay, so let's take a solution and see what this gives us in turn. So we have solution. Okay, the first thing we're going to do here is to rewrite the radicals we have here. The one on the left-hand side and that at the right-hand side. And so rewriting this is going to give us a 3 to the power of x all raised to the power of 2, or in bracket raised to 1 all over 2. This is equal to our 3 to the power of our x raised to 1 all over 2. So we succeeded in eliminating the radical we have here now. Okay, so what we do here, if you take a look at this expression, we can use it to multiply this, right? Good. We are applying the law of the first law of we're going to operate here with is your a to the power of m times n. This is equals to a to the power of your m in bracket then raised to n. So if we do that, this will multiply this expression we have here. So this is going to give us our 3 to the power of our x all raised to the power of 2 all over 2. This is equal to our 3 to the power of x raised to 1 all over 2. If you check the base numbers, they are the same. That on the left-hand side and that on the right-hand side, they are both the same. And so it means we can equate the exponents, right? So if we equate this is going to give us here our x to the power of 2 all over 2 equal to our x to the power of 1 all over 2. Easy. But we're still having a fraction on the left-hand side of the equation. So we eliminate the fraction by multiply with this, which is 2. So this gives us here our x to the power of 2 all over 2 times 2 equal to our x to the power of 1 all over 2 times 2. This and this will leave. So we are now left with x to the power of 2 is equal to 2 into x to the power of 1 all over 2. Wow. So let's check out what this comes out with. Now, look at this power here. And look at this. This is another form of a radical, right? Good. So we have to eliminate this radical again. But we have to take the opposite of this, which is the square. So let's square this side of the equation and this side of the equation. So if we square both sides of the equation, meaning we're raising this to the power of 2, we're also raising this to the power of 2. So with this, we can use this to open up this according to this law. So this is going to give us our x to the power of 4 equal to, if we use this to multiply this, what happened? These two will go with these two. So we are now left here with our x here. And again, these two will affect these two here to give us 4. So we're going to have here 4x, right? Good. So yeah, we move this quantity to this side. I've said this in many of my videos that when you have an expression of this kind, never you cancel out x or never you divide by x. And so we move this quantity on the left-hand side, sorry, right-hand side to the left-hand side. So this is going to give us x to the power of 4 minus 4x is equal to 0. We cannot factor out x here. So if we factor out x, it's going to give us x to the power of 3. It will be 3, rather. So reduce to 3, then minus 4, those bracket equal to. So from here, we just have to consider the zero property, which says that our a, okay, let's use a times our b is equal to 0, and our a will give us 0, or our b will be equal to 0. So yeah, we're taking case 1, we're going to have x1 is equal to 0. So this is the first root, or the first answer to this challenge. But let's check if this will satisfy the original equation. If I put in 0 here, 0 to the power of 2 will give us 0. So 3 to the power of 0 will give us 1. And square root of 1 will give us 1. And so if I put in 0 here also, the square root of 0 will give us 0. The 3 to the power of 0 will give us 1. And so 0 is a root that satisfies the original equation. Now let's go ahead and solve for this. This is where we have an interesting mathematics or interesting expression. Okay, now if we decide to move this to this side, and we take the cube root of both sides, we're going to come up with just one root. But here we are expected to look for 3 roots. And so what do we do? If we decide to write this as 2 to the power of 2, that will give us a power of 2. And here we are having a power of 3. And so there is no correlation between the power of 3 here and that of 2 here, as far as this expression is concerned. So we try to rewrite this to the power of 3. And how do we achieve that? We raise the power of this very guy here to the 1. Although we have divisible 1 here. And so rewriting that one, we go to say 3 all over 3. So we're going to rewrite this as our s to the power of 3 minus our 4 to the power of our 3 all over 3 equal to 0. If we consider this property, then we can shift in this 1 all over 3 inside here, right? So if we do that, this is going to give us our s to the power of 3 minus our 4 all raised to 1 all over 3 all raised to power 3 equal to 0. Wow. So with this, what we do, we now have what we call our difference of 2 cubes. So it says that when you have your x, okay, so let's use a, we have your a to the power of 3 minus b to the power of 3. This is equal to a minus b, or in bracket, your a squared plus your ab plus your b squared. So if we rewrite this in that format, we're going to have here bracket open x minus 4 to the power of 1 all over 3 close bracket, our x to the power of 2, then plus, we're going to have 4 to the power of 1 all over 3, then x of x, then plus our 4 to the power of 1 all over 3 all raised to the power of 2. Everything equal to 0 here. Okay, so we're going to have another case here now. So we have case 2. So our case 2, we're taking our x minus 4 to the power of 1 all over 3 equal to 0. So we now have our x2 is equal to 4 to the power of 1 all over 3. Now we can reduce this base here. In other words, we can write this as 2 to the power of 2 and use the 2 as the power to multiply the exponent here. And so we're going to have this to be something nice here. So we're going to have our x2 is equal to 2 to the power of 2 all over 3. So this is the value of our x2. You can go ahead and substitute that into this place. And when you do that, you see that it will satisfy this challenge here. Okay, so let's take the next one now. So we got to 2 roots as far as this challenge is concerned. So the next one now is this. So here we have our s to the power of 2, then plus our 4 to the power of 1 all over 3x, then plus our 4 all raised to the power of, okay, let's keep this in this format, all raised to the power of 2. This is equal to 0. So here we have a quadratic equation. I want to use the formula method to solve for this. It is pretty easy. So we have our x, our formula says minus b plus minus the square root of our b squared minus 4ac all over 2a. Substituting, what is our b? Our b is this. So we have 4 to the power. So we have a minus here. Okay, so we have minus our 4 to the power of 1 all over 3, then plus minus the square root of our 4 to the power of 1 all over 3 all raised to the power of 2, then minus our 4 times our A is 1, so we have 1 times our C is this. So let's put down our C as 4 to the power of 1 all over 3 all raised to the power of 2. Everything all over 2 times 1. So 2 times 1 will give us 2. All right, so we are almost there. Okay, so let's look at this carefully. We don't have to factor out this, okay? All we just need to do is that what we have here, same thing we have here. So we can factor this out. So doing that, this will give us minus 4 to the power of 1 all over 3, then plus minus the square root of our 4 to the power of 1 all over 3, all raised to the power of 2. If we use this to divide this, we are left with 1. So we're going to have here 1. If we use this to divide this, we are left with our 4 times 1, which is 4. Easy. Everything all over our 2. Yeah. So this is a square root. This is our square. So this can come out. So this is going to give us our x will now be equal to minus 4 to the power of 1 all over 3, then plus minus our 4 to the power of 1 all over 3 to the square root of 1 minus 4. Everything all over our 2. Easy. So if we carry out this expression, this is going to give us our minus 3. And we know that the square root of minus 1 is equal to our iota. So we can write minus 3 as the square root of minus 1 times the square root of 3. And so rewriting this is going to give us, yeah, this and this are common. So we can factor this out from here again. So doing that, this is going to give us our minus, and let's still keep this without factoring it out, minus 4 to the power of 1 all over 3, then plus minus 4 to the power of 1 all over 3, then, okay, let's bring in our iota, 3, then all over 2. Okay, so we can still simplify this result down, okay? So we simplify this down, this is going to give us, here we're going to have our 2 to the power of 2 all over 3, then in bracket, if we use this, whatever we have here, this expression we have here is the same thing as this. Okay, so if we use this to divide this, we are left with minus 1 plus minus, then this we are left with iota root 3, close bracket, all over our 2 raised to power 1. So we can use this and this to divide out. So if we divide out, this is going to give us our 2, which is, we're dealing with the powers 2 minus 1. So this is going to give us minus 1 all over 2 at the exponent. So let's erase this and continue on this side. All right, so from here, we're going to come up with our 2. Let's separate this. So we're going to come up with our 2 to the power of minus 1 all over 2, then into our minus 1 plus minus iota root 3, close bracket. And so we can shift this down because of this. And so this is going to end up giving us minus, okay, let's just put in the minus straight without putting in bracket. So we're going to have minus 1 plus minus iota root 3, everything all over root 2. But we have to rationalize this. So if we rationalize this, we multiply by root 2. So if we multiply this side by root 2, multiply this side by root 2. So let's just put it down. This all over root 2. Okay? So if we multiply out here, we're going to have our x3. This is going to give us our minus root 2 all over 2. Then plus our, because we're going to have root 2 times root 3 here, so it's going to give us root 6. So we have iota root 6. Okay? Then all over 2. And our x4 will give us here minus root 2 all over 2 minus iota root 6 all over 2. So in all, we have 4 roots to this challenge here. 4 solid roots to this challenge, of which 2 of them are imaginary roots, then 2 are real roots. So this brings us to the end of today's math class. Hello and welcome to today's smart class. We have a nice exponential challenge here. The question is x to the power of x equal to 4 to the power of x plus 4. What then is the value of x that will satisfy this challenge here? Now, if you look at this, it appears easy, but how do we solve this algebraically? If you are not too conversant with the laws of indices and some manipulations of exponents, then you would be able to solve this. So let's see how we solve this algebraically. So we're taking our solution first. So we have our solution. All right. So we just have to rewrite this side of the equation, which is the right-hand side of the equation, applying the law of indices. So the first law we're going to apply says that when you have your a to the power of your m plus n, this is equal to your a to the power of your m times your a to the power of your n. Okay? So we are having the bases to be the same, and so we have a multiplication there. We add the powers. So we rewrite this. This is going to give us x to the power of x equal to our 4 to the power of x times our 4 to the power of 4. Okay, so let's carry the terms that have x to the left-hand side of the equation. And how do we do that? We divide by 4 to the power of x. So if we divide this by 4 to the power of x, we equally divide this by 4 to the power of x. So this will live with this. We are now having another law play out again. But let's write this expression out. We're having x to the power of x all over 4 to the power of x is equal to, here we are now having 4 to the power of 4. Okay, now see what we now have here now. We are having x to the power of x and 4 to the power of x at the bottom. So we succumb to a law which says that when you have your a to the power of your m all over b to the power of your m, this is same thing as a all over b all raised to the power of m. And so we can rewrite this side to give us here our x to the power, x all over 4 all raised to our x here equal to, we are having 4 to the power of 4. Okay, so the next thing we're going to do here is this. Let's try to eliminate this x as the exponent. And what we do here, we're going to multiply or raise both sides of this equation to 1 all over x. And so we're going to write this. This is going to give us our x all over 4 all raised to the power of x. Then in bracket, raised to the power of 1 all over x. Then we do same thing here. Our 4 to the power of 4 all raised to 1 all over x. Now look at this expression here. We apply the third law of indices here. The law which says that when you have your a to the power of m times n, this is same thing as a to the power of m, or in bracket raised to n, which is also a to the power of n, or in bracket raised to m. So we can use this to open this because this is power, this is power. So if we multiply out, this and this will leave. So with that, we're going to have a very nice expression from this. How? And so this is going to give us x all over 4 only equal to, we also use this to multiply this, and this is going to give us our 4 to the power of 4 all over our x. Easy. Wow. So with what we have here now, we're going to do a simple substitution here. So how? Here, let's take a substitution. Let's say let's take t, okay? Let's our x all over 4 be equal to t. Look at the relationship between this and this power here. The x here is at the numerator and 4 is at the denominator. But here we are having 4 at the numerator and x at the denominator. And so this is more or less a reciprocal of this. So if we are saying let x all over 4 be equal to t, If we decide to find the reciprocal of this expression, we're going to come up with 4 all over our x will now be equal to 1 all over t. Easy. Good. So with this we have in here now, let's substitute these two quantities in our equation here. So this equation will now become our t will be equal to, our 4 remains here, 4 all raised to the power of 1 all over t. Are we learning something here? Good. So with what we have here, we want to eliminate this power again. So how do we eliminate this? We're going to raise the powers here to t. Raise this one to t. And so this is going to give us our t to the power of t. This is equal to 4 to the power of 1 all over t, all raised to the power of t. Now we come to this law again. So if we apply the law to this other side, what happened? Then this, we live with this. Okay, so when we have this out, here we're going to have our t to the power of t equal to 4. Good. Now look at 4. 4 is a perfect square. So we can write 4 as 2 to the power of 2. So rewriting this is going to give us our t to the power of t is equal to 2 to the power of 2. Look at the left-hand side of the equation, t to the power of t. Okay, so this variable to is raised to its own self, then this constant raised to its own self. So we can equate the exponent or the base. And so it all means that our t is equal to 2. Now let's keep this value here. We do not have t in the initial equation, so we go to where we say let our x all over 4 be equal to t, so that we can get the actual value of t. So from here we can now say recall that our x all over 4 is equal to t. So what is our t? Our t is 2. So we put 2 in place of t. So it is going to give us our x all over 4 is equal to 2. When you cross multiply, this is going to give us x is equal to our 4 times our 2. So we have, therefore, x is equal to 8. So 8 is the answer to this wonderful exponential equation. But let's see if this actually satisfies this equation, or if the solution is an extraneous one. So take our check. So we have our x to the power of x is equal to our 4 to the power of x plus 4. So let's go ahead and put our 8 in place of x here. So this is going to give us our 8 to the power of 8 is equal to our 4 to the power of 8 plus 4. So we now have 8 to the power of 8 is equal to our 4 to the power of 8 plus 4 will give us 12. So we have here 12. If you compute 8 to the power of 8, what will that give you? This is going to give you 16, 7, 7, 7, 2, 1, 6 equal to, and again, if you compute this will also give you 16, 7, 7, 7, 2, 1, 6. It's a large figure. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So this gives us 16,777,216. Okay, and so this shows that the answer we solve for, which is x equal to 8, actually satisfies the original equation. So give the video a thumbs up if you find this video facilitating, and you have any question with regards to the steps I apply here, then drop it in the comment section. Again, if you have a better way of solving this, an alternative way of solving this challenge, drop it in the comment section so that we can equally learn from you. Hello, welcome to today's class. We have an algebraic equation before us here. It's a nice one. The question is a times a times a times a all over a plus a plus a plus a equal to 16. What is the value of a here? Now, at first, you can tell straightforward the number of roots we are going to get from this challenge here. Okay, here we have 4. And at the bottom, we are also having 4. So I never think we're going to get 4 roots from this challenge. One of the variables at the bottom, we cancel out one at the numerator. And so we are expected to solve for 3 roots here. Okay, so let's take our solution and see how we solve this or how we go about this. So this will now give us, because here we have the same base number and we have multiplication. So the powers here are just 1, 1, 1, 1. And so we add the powers together. And so this is going to give us our a to the power of 4 all over. Yeah, the variables are the same too. And we have the summation sign here. So we can add them together. And that will give us our 4a equal to 16. Easy. Now we can rewrite this expression by separating this 4 out here. So this is going to give us 1 all over 4 times a to the power of 4 all over a. This is equal to 16. So we have a division sign here. The variables are the same, but the powers are different because here we have invisible 1. So we apply the law of indices, which says that when you have your a to the power of m all over a to the power of n, subtract the powers. So we're going to have a to the power of m minus n. So we can subtract 1 from 4 here, and this will leave the system, and that will give us a to the power of 3. So we have 1 all over 4 times a to the power of 3 equal to 16. So the next thing we do here is just to eliminate this 4 here. And how do we go about that? We multiply both the right-hand side and the left-hand side of the equation by 4. So this is going to give us our 1 all over 4 times our a to the power of 3 times our 4. This is equal to 16 times 4. So this and this will leave. We're now left with our a to the power of 3 is equal to 4 times 6 will give us 24. 24, put down 4. There 4 times 1 will give us 4. Plus the 2 you carry gives us what? 6. So that's going to give us 64. All right. Now, if we decide to take the cube root of both sides of this equation, we're going to come up with just 1 root. But I said we are to look for 3 roots here with this power we are having here. And so we move this side of the equation, which is this quantity on the right-hand side, to the left-hand side. And so this is going to give us our a to the power of 3 minus 64 equal to 0. So having this, what comes to mind is, can we express 64 in a number that we can raise to 3 to give us 64? Yes. If we raise 4 to the power of 3, that will give us 64. And here we are having a power of 3. So let's go ahead and do that. This is going to give us a to the power of 3 minus, rather, this minus 4 to the power of 3 equal to 0. So seeing this kind of expression, what comes to mind? We have what is called the difference of 2 cubes. And what does it say? It says that when you have your x to the power of 3 minus y to the power of 3, this is equal to your bracket typing x minus y close bracket, your x to the power of 2 there plus our x, y, there plus our y to the power of 2. Nice one. So this expression we have here now is in this form. We want to take it to this form here. So let's go ahead and rewrite this. So this now implies that our a, bracket open a, minus our 4, the close bracket, a to the power of 2, the plus our 4a, the plus our 4 to the power of 2, close bracket, equal to 0. Okay, so we are having this bracket times this bracket equal to 0. We apply a rule which says that your m times n, this is time please, sorry, equal to 0. It means that our m is either equal to 0 or n is equal to 0. So we call this the 0 property. So with this, we're going to have first case and second case here. So we have case 1. Case 1, we're going to have bracket open a minus 4 equal to 0. Then if we open this, it's same thing as a minus 4 is equal to 0. Send this to this side, so we have a is equal to 4. This is our a1, the first value or the first root that will satisfy this challenge is A is equals to 4. Okay, so let's go ahead and look for the other two rules because we have 3. We have to look for 3. We've got to 1, and to get the other 2, we applied this rule, or we take this as the second case scenario. So we have here case 2. So case 2, we have our A to the power of 2 plus 4A, then plus 4 to the power of 2 is 16. So we're going to have here, or let's leave it at this form. Okay, no problem. We're going to work with this like this. All right, so this is a quadratic equation. We're going to use the formula method. So using formula method, we have our A is equal to our minus B plus minus the square root of B squared minus 4AC, everything all over our 2A. So let's quickly bring out the value of A, B, and C. Our A is the coefficient of A squared, which is equals to 1, right? Okay, so we have 1 here. Again, this A is different from this very A here. Okay, so don't be confused with this. So there, our B is equal to the coefficient of just A, so we have here 4, and our C is the constant term, which is 4 to the power of 2. So we want to impute this into this system. So we have our A is equal to minus, where's our B? 4. So we have here minus 4 plus minus the square root, our 4 to the power of 2 minus 4 times 1 times 4 to the power of 2. Everything all over our 2 times 1. Wow. So how do we simplify this? Let's bring out 4 to the power of 2 from here and here because they are common. So this is equals to, this is the reason why I said no need. Simplify this. So this is going to give us minus 4 then into the square root of our 4 to the power of 2, bracket open. If we use this to divide this, we are left with 1. Then minus, we use this to divide this, we are left with 4. Close bracket, everything all over 2. Okay, so let's continue on this side again and see what this gives us in turn. All right. So this is our square root here, and so we are having 4 to the power of 2. So this 4 can come out. So this is going to give us our A is equal to minus 4 plus minus 4 here, because here we are having square here, and it will take care of the square root here. Then under here, we are now left with minus our 3, because 1 minus 4 will give us minus 3. Then all over our 2. Wow. So we can rewrite this. Remember that the square root of minus 1 is equal to iota. So we can bring iota into the system. And here we can factor out 2 because we're having 2 at the denominator. So this is going to give us A is equal to 2 into minus 4 will give us minus 2, the plus minus 2, the iota root 3, close bracket, all over 2. So this and this can leave the system. So we end up having our A is equal to minus 2 plus minus 2 iota root 3. Easy. Okay. We can still simplify this down to get our A2 and A3. And so let's write out our A2. Our A2 is going to give us, if we decide to bring out 2 from here, that's going to give us 2, open bracket, minus 1 plus the square, our iota to the square root of 3. Then our A3 will now give us 2 into minus 1 minus I root 3. So these are the other 2 roots, but they are imaginary roots. It is only A1 that is a real root to this challenge. So this brings us to the end of this math class. you've learned something from this video, do not forget to give this video a thumbs up. Remember, we love you. Thank you for being there all the time. Again, you're welcome to another math class. Here we have this challenge here. It's a simple exponential challenge. The question is 5 to the power of x plus 1 equal to 2 to the power of 3x. What is the value of x here? So this is pretty easy if you are acquainted or familiar with some laws of indices and that of logarithm. So we're going to use these two interchangeably or together. We're going to use this. So get our solution. So the value of x here is x. Now we just have to rewrite this left hand side and this other side. Let's just keep it like this. So we're applying the law which says that when you have your a to the power of your m plus n, this is equal to a to the power of m times a to the power of n. Okay, so this is going to give us our 5 to the power of x times our 5 to the power of 1 equal to 2 to the power of 3x. Easy. All right, now we want all the terms having x as the exponent to be on one side, and so we want to cancel out this. So we're going to divide through by 5 to the power of x. We equally divide this by 5 to the power of x. So this and this will leave. So we have 5 is equal to our 2 to the power of 3x, then all over our 5 to the power of x. Good. Let's turn this expression in other words. Let's move this to this side, move this to this side. And rewrite these powers here, or this expression we have here. We know that if you have your a to the power of m all over your b to the power of the same exponent, this is a all over b all raised to the power of m. So if we rearrange, we're going to have here 2 to the power of 3, okay? Then all over 5 all raised to the power of our x is equal to r5. Easy. So at this point, we just have to either take log to base 10 or we ln both sides of the equation. So let's take our ln. So we're going to have here the ln of bracket open 2 to the power of 3 all over 5 close bracket all to the power of x is equals to the ln of our 5. Let's put this in bracket. So here comes the property of logarithm we're going to apply. We call it the power law of logarithm, which says that when you have the ln of your a to the power of b, move this b back here. So this is going to give b times the ln of a. Okay? So with this, we can rewrite this. We want to move this exponent back here. So we're going to have x times the ln of bracket open 2 to the power of 3 all over 5 close bracket is equals to the ln of our 5 close bracket. What do we do next? It's pretty easy. So let's divide through by the ln of our bracket open 2 to the power of 3 all over 5. So if we do that, we're going to have here our x will now be equal to the ln of our 5 all over the ln of our bracket open 2 to the power of 3 all over 5 close bracket. Here we apply another law of logarithm. We call it the division law, which says that when you have your ln of bracket, your a dividing b, this is equal to the ln of a, then minus the ln of b. Okay, so we can rewrite this, right? So this is going to give us the ln of our 5 bracket all over the ln of 2 to the power of 3, then minus the ln of our 5 here. Okay, so applying the power law, this is going to give us our x will now be equal to the ln of 5 bracket all over 3 times the ln of our 2, then minus the ln of our 5 close bracket. Okay, so To get the numerical value, input this in your calculator, input this in your calculator. When you simplify, you have a numerical value. And when you put the numerical value into this system, that's going to give you an approximate value or approximate answer. So this is the final answer to our challenge. So this brings us to the end of this class. If you have a question with regard to this, drop it in the comment section. We meet with you there. Thank you for watching Online Maths TV. We see you in our next class. Hello, great family. Here we have this question before us here. It's a different question from our normal question we normally solve on this channel. So it's an integration, okay? So the question is the integral of 1 all over x times the ln of x dx. What is the value if we are to integrate this, or how do we integrate this? So let's take our solution. Solution. Although this is a simple one, okay? So we have here the integral of our 1 all over x times the ln of x dx will now be equal to what? So the first thing we're going to do here is to do some substitution here. So we're going to say let our u be equal to the ln of x. So we say let u be ln of x. So rewriting this expression, we're going to have here the integral of 1 all over our x times our u, the dx. Now let's look at this. We can equally rewrite this, separating this x from this, because this has changed the system already. So rewriting this is going to give us the integral of our 1 all over x times 1 all over u dx. Now, let's come back to where we did a substitution here. We said let u be equal to the ln of x. Okay? So if we therefore differentiate this expression here, so we're going to have our du dx, right? Du dx will now give us here our, if you differentiate ln of x, which is ln x, is going to give us 1 all over x. So we cross multiply, or we multiply by the x. So we're going to have our du is equal to 1 all over x, then dx, right? So yeah, we have to make the x the subject of the formula also. So our dx from here will now be what? Our x times du. So we have here our x times our du. All right, so let's come to our expression here now. We're going to substitute for our dx here. Look at our dx. Our dx is equal to x times du, right? So if we substitute, this is going to give us the integral of 1 all over x times 1 all over u, then times our x, then times our du. Now look at what we have here. We're having x at the bottom here. We're having x at the exponent. So this and this will leave. So we are now left with our integral of our 1 all over u du. So from here, if we integrate this is going to give us the integral, ln our absolute value of u, okay, of u, then plus c. But what is our u? Look at what we said we should put our u. So we have u to be the ln of s. So if we do this is going to give us our ln of the absolute value of ln x, then plus our c. So in conclusion, we can say that therefore the integral of our 1 all over our x times the ln of x dx is equal to the ln of the absolute value of ln of x, then plus rc. Wow. So this is the answer when you integrate this expression here. So if you learned something from this video, give the video a thumbs up. See you in our next class. We'll be bringing more of these kind of challenges on your way. See you in our next class. Till then, keep winning.